For lesson 3, we're going to start to learn some new terminology and vocabulary words that are associated with circles. So for the opening exercise, we're going to write down a couple things that we know about circles. So far, we've done the equation. I want to leave that piece out. I'm talking about kind of some other properties that we know about circles. Most of the time, the things that come to people's mind are 360 degrees in a circle. We have all points on the circle are equidistant from the center. All right, and that big long definition has a word, and that's our radius. Okay, so all points on the circle are equidistant from the center, and then that the diameter is double the radius. Okay, so that's things that people usually come up with. And those are going to start to help us a little bit more as we go through this lesson. So a couple vocabulary words. Radius is the first one. So the radius, kind of like we just described, is the distance from any point to the center of the circle. Okay, so my diagram here, I'm going to estimate my center. I'm going to call it O. So circles are defined, or circles are named by their center point. So in this case, this would be circle O. And then you can pick a point anywhere you want. We'll call it R. And that distance from O to R is going to be our radius. Okay, so that one's pretty easy. Everybody usually knows what a radius is. A chord is a line segment connecting any 2 points on the circle. Okay, so if you pick a point wherever you want, a lot of times people try to draw a diameter. And that is true, but a chord is much less specific than that, okay? So there would be chord AB, all right? It connects any 2 points that are on our circle. And then the third one is our diameter, which is basically just a more specific chord. So it's a chord that passes through the center, okay? So we obviously couldn't draw our chord the same way, or our diameter the same way we drew our chord above, because we have to make sure that we are passing through the center. So that there would be our diameter, and you could call it AB. Some people choose to use 3 letters and use the center point, but you don't have to. So chord and diameter are very similar. Diameter is just a little bit more specific. So exercise 1, identify each segment inside the circle below as a radius, a chord, or a diameter. So AD, I see AB, and I see AC. So AD, AB, AC, those 3 all go together. Those 3 are our radius. Okay, so 1, 2, 3. Those 3 are going to represent our radii. Okay. Now, what else do we see? Well, I see dB. So dB right there is going to be our chord. Okay. So that's a chord because it connects any 2 points on the circle, but it does not pass through the center. And then the last one would be DC or CD, kind of up to you. And that is going to be our diameter, all right? And again, that's going to be our diameter because it connects 2 points on the circle, but it also passes through the center. So now we want to explain why triangle ABD has to be isosceles, all right? And I marked what should be pretty obvious what the 2 congruent sides are. And this goes back to one of the things we wrote down in the very beginning. Since all the points on the circle are equidistant from the center, all radii in the same circle are congruent. Okay, so that means that AD must be congruent to AB because both are radii. All right, so since both are radii of the same circle, that means that that triangle ABD has to be isosceles. In circle O, points A and B are located on the circle. The length of OA is 2x plus 19. Determine the length of OA if the chord AOB is 37. All right, so a couple pieces of information here. The first thing we want to do is we want to draw a circle. And we'll put our center in there. So it says in circle O, so that means our center point is circle O. Now we could maybe guess where A and B are, but this is the key. Because it's a chord that passes through that center point, that means it's a diameter. Okay, so A and then B. All right, try to estimate them on the opposite sides of that circle as best as possible. And that's what we get. All right, so it says the length of OA, which is our radius, is 2x plus 19. We want to determine the length of OA if the chord AOB is 37. So realistically, do we have to solve for x here? Because if we're looking for the length of our radius and our diameter is 37, we know that the radius is half of that. So our radius here is going to be 18.5. All right. It didn't ask you to find for x. I didn't ask you to find x. It wanted you to determine the length of OA based on the fact that you know your diameter. All right. And since we went over in the very beginning, the diameter is twice the radius. We cut it in half and we get our radius OA. All right. A couple more vocabulary words. All right. Arc. Arc is the distance between any two points on the circle. All right, so A and B. So that distance around the outside is going to be our arc. All right, it's almost like part of the circumference of the circle. All right, so you can almost think, remember when we did arc length, we found the distance around part of a circle. It's kind of the same thing here. All right, so the arc is the distance between any 2 points on that outside edge of the circle. Minor arc, okay, is any arc less than 180 degrees. All right, so any arc that is less than 180 is considered a minor arc. All right, and I'm going to draw the last one there to make it pretty clear because it's obvious that A and B are less than halfway around the circle. Well, if a minor arc is less than 180, then a major arc is any arc greater than 180 degrees. Okay. Typically, these have 3 letters. Okay. So the symbol for arc, and I'll go back up to the beginning here, is you put like a little hat on it. Okay. So arc AB, then we have arc AB. So you'll see a minor arc and that regular one are usually exactly the same. The major arc usually requires 3 letters, okay, because that tells you to get from A to B, it wants you to pass through C. So that means you have to go around that backside. So we want to name the major and minor arcs with endpoints A and D, okay? So let's take care of the minor arc first, because that is very simply AD. All right, so when you just have the 2 letters, you're going to take the shortest distance to get there, which is that AD right there. Now, if we want to name the major one, there are 2 letters in between. There's B and C. It doesn't matter which one you pick. I usually just pick the first one. So that would be major arc A, B, D. Okay, you could put all 4. You could put A, C, D. It's the same thing, but you do not have to put all the letters in between them. Once you tell it to go A, B, D, it obviously has to pass through C. Name the major and minor arcs with endpoints A, B. So, again, Minor typically just includes the two letters. That's the short distance between A and B. And then major would be A, D, B. All right, again, I'm picking the first letter that I see on that back way from A to B. Describe what arc BCD is to the circle. So this is going to be very important here. So BCD, what is that? Well, that's half a circle, otherwise known as a semicircle. Okay, and a semicircle should always be synonymous with 180 degrees. Okay, so a full circle 360, so a semicircle is 180. So a little bit more vocabulary here. Arcs are important concepts when working with circles. They allow us to determine the portion of the circle where each sector represents. Another way for us to determine the portion of a circle is with the angles that creates the arcs. There are two simple types. There's the central angle and an inscribed angle. Okay, so a central angle is exactly what it sounds like. It's an angle whose vertex is at the center of the circle. Okay, so again, I'm going to put in the letter O here. A, O, B. So if we were to create an angle out of that, okay, that would be angle AOB, all right, central angle. Now the next really important thing here, and I'll put it in red, is the central angle equals the arc. Okay, so for example, if arc AB is, let's say, 137 degrees, that means angle AOB is also 137 degrees. So the arc that central angle opens up to is going to have the same number of degrees in it as its central angle. All right, so commit that to memory. Central angles are equal to their arcs. So now the second type is an inscribed angle. So it's an angle whose vertex is on the circle. Okay, so I'll put my letter O back in here again for my center. But now in this case, I'm going to have an inscribed angle that looks kind of like this. So you can see the vertex C, angle ACB, that vertex is on the circle. Okay, so that's called an inscribed angle. Now central angles equal their arc. Inscribed angles equal half their arc. Okay, so I'll put a better theta in here. Now, if we have the arc at, let's say, 80 degrees, that would make angle ACB 40 degrees. Okay, because inscribed angles are going to be half of their arcs. All right, so similar rules, but you want to commit the two different ones to memory for central and inscribed angles. So let's take a look here. In today's lesson, we're going to look at some of mainly our central angles. We'll get a lot more into our inscribed angles as we move on into the next lesson. But exercise 4 says circle B is shown below. What do you know about this, or use what you know about circles to determine the measure of each angle and arc below when the measure of angle EBC is 65 degrees. So EBC is 65, and arc DE, so that short distance between D and E, is 100. Okay, so there's a lot of different ways you can go with this, and what I'd like you to do is pause the video for a minute and try to fill out as many of these as possible. All right, and you'll see here it's got angle ECB twice, and I don't really know why, so you can just cross out one of those. But pause the video for a second and see how many of these you can figure out. So if we want to find angle ECB, that's this little angle up here, well, we have to use what we remember about isosceles triangles, the fact that these two angles that are missing in it are the base angles. So that would be 180 minus 65 gives us 115. we divide that by 2, and that gives us an angle of 57.5 degrees. All right, so that angle right there is 57.5, right? And that was just isosceles triangle rules based on the fact that we have 2 radii. What about angle ABC? Well, this has nothing to do with circles. This is really just, well, ABE is a line, and these 2 angles are supplementary. So if we go back here, 180 minus 65 gives us our 115. All right, and again, that's just supplementary angles right there. Angle BAC. Okay, well, we could do our same isosceles triangle rules that we did before, except now it'd be 180 minus 115, which is 65. And then if we divided that 65 by 2, we'd get 32.5. So angle BAC is 32.5 degrees, okay? And again, you could actually, I probably should have done this in the other one, since you know these are isosceles, you can just fill in the other base angles as well. All right, so now that we've filled in all those angles here, it wants to know A, C, E. So we're going to take the 32.5 and the 57.5 and add them together, and what do we get? We get 90 degrees, okay? So all of ACE, which puts both of those 2 angles together, gives us 90. So now as we look around, we want to know some of our arcs. So wants to know arc AC. Well, how do we know that? If our central angle is 115, that means our arc between those 2 points is 115 degrees. Okay, arcs and central angles are exactly the same. Arc CE. So arc CE is the same thing. What's its central angle? 65. So what is its arc? 65. Okay. Now AD doesn't have like a central angle or anything that maps it, but if you look at ABE here, it's a diameter which creates a semicircle, which means arc ADE has to be 180 degrees. Well, if we know from D to E is 100, and we subtract those 2, then we know that arc AD is 80. All right, so just some circle rules here that go with pretty much basic arithmetic. But that's how we apply some of our properties about circles to help us fill in some of our missing angles and arcs.